course is called Introduction to Complexity, for Chaos to Complexity. So dynamical systems is a field that's fairly recent. It was more or less born in the 60s. And chaos, the ideas behind chaos theory came about really in the 70s and 80s, and then became the field that is now known as the study of complex systems. So one of the advantages of this field is that it produces many compelling graphics. So this is a strange attractor, of which we'll be talking about later. And these are bifurcation diagrams, which we will also be seeing quite a lot of. Now, the basic question of this course is, where does complex behavior come from? So if I showed you this diagram, which is the time evolution of some quantity, let's say the time evolution of a population of rabbits, for instance, or the fluctuations in the Earth's average temperature. So if you look at this diagram, what kind of system would you assume gives birth to this, basically? What kind of dynamics would you say allows for this fairly rough, ragged, jagged evolution with, if you just observe this for a moment, you see there are definitely still patterns, nothing quite repeating, but some patterns. For instance, you'll notice that every time the line almost reaches 1, it immediately afterwards goes down quite low. But in between, apart from a few of these noticeable patterns, it really is the case that the evolution is unpredictable, and it's known as chaotic. So my question to you is, well, what kind of a system would produce this, right? What would be the main characteristics of such a system? Does anybody have any, not even guesses or ideas, just assumptions as to what this might look like? Well, I think most people would say, given how complex the dynamics are here, non-repeating patterns, very jagged evolution, you'd probably assume that it came from something like that, right? A complex system. So this is the Brotherton diagram, which was introduced by NASA to study the Earth system, basically. So as you can see, it is very much a complex system, right? So you have here driving forces, so the energy coming from the sun, volcanoes, which have an influence on stratospheric physics. Then you have all the water cycles. So you have marine biochemistry interacting with global moisture. You have, atmospheric physics. You have troposphere chemistry, and human activities over there, which affect all of this in complicated ways, right? So, for instance, like CO2 emissions will affect atmospheric physics. Atmospheric physics will then feed back into ocean dynamics. Ocean dynamics will feed back into global moisture. And so, if we go back to this graph, right? If this was, say, the evolution of a population of seashells or rabbits or whatever, then you might assume that, yes, there are complicated dynamics at play which mean that, different feedback mechanisms that mean that the population will evolve in this very haphazard, very jagged way. But the thing is, this time evolution diagram doesn't actually come from a complex system. It comes from this equation. So this, even if you've done essentially no mathematics, this is just a simple map. This tells you that for any value of x, then to get the next value of x, you will just multiply by r, then multiply by 1 minus x. This simple equation, which as you'll see is known as the logistic equation, is what is used to generate this time series. So that's essentially the main insight of chaos theory, right? Is that you don't actually need a complex system to generate complex behavior. Very complex behavior can emerge from actually very simple systems. In particular, the logistic map being a textbook example. So this is really my kind of pitch for the course, right? By the end of it, you should understand the concepts and history behind chaos theory in the field of complexity. I don't expect any of you to be familiar with the mathematical background of chaos theory, which is quite abstruse. And I think really, yes, I want you to get a feel for the concepts and the history. Then also, I want you to become more attuned to the different types of models used to describe such systems. What I mean by that is that basically most of physics and any science that takes any kind of inspiration from physics, so for instance economics, or earth science systems, these tend to work with very rough and simplified models of reality, basically. And what you always want to be finely attuned to is the difference between your model, your model's predictions, and reality, and in particular, the shortcomings that are intrinsic to your model and the assumptions that are the foundation of such models. So this is also, I guess, it's a course on chaos, but also really a course in learning how to interpret models, really, and what kind of models exist, and how do they behave generally. The kind of take home by the end of this lecture, and really by the end of the series of lectures, will be that, as I've already shown you, complex behavior does not imply a complex system. A simple system can have very complex behavior. And inversely, a very complex system can have very simple behavior. So this is the case to some extent of the Earth system, for instance. So if we go back to the Bretherton diagram, you see there are many, many interactions between like CO2, atmospheric physics, human activities, etc. But we know that the interaction, at least for the short term, between like CO2 in the atmosphere and, say, temperature is pretty straightforward. The more CO2 is in the atmosphere, the more the temperature rises. And it does so in a fairly proportional way. So, very complex system, but actually very simple dynamics, at least in some aspects. So this is the first thing. Complex behavior and a complex system and a complex model are not necessarily the same thing. The other thing, and this is a concept that's perhaps not very easy to grasp right now, but which by the end of the course I should hope that you have some intuitive understanding of, is the idea that very different models can behave very similarly. So in physics this has a name. This is called universality. And it was really discovered in the context of two different fields, so the study of dynamical systems, as well as the study of, weirdly enough, phase transitions, which is the study of, how the physical state of things change, from water to vapor, so from liquid water to vapor, etc. So universality is the idea that very different phenomena can actually have very similar descriptions and can be interpreted with very similar ideas. So this is a rough overview of the course as I see it now. I think it's bound to evolve a little bit as I come to know your backgrounds better, because inevitably what's going to happen is that sometimes I won't necessarily be pitching it at the right level right away. So I want there to be some interaction, some feedback, because I need to know where you're at in order to really follow a course that has a sort of coherent structure for you. So the first session, which is this one, basically, is an introduction to the course itself, and I'll also give you a short historical background of chaos theory and complex systems. I'll also kind of touch upon a smattering of questions we'll be asking ourselves throughout the course. Then, in the second and third sessions, we'll be doing a kind of like bestiary of physical models. What I mean by that is that some of the more surprising insights of chaos theory and complex systems come from essentially a physicist's own shortcomings. In that basically, as a physicist, you're trained to see the world in a very particular way and use a very particular type of family of models to understand reality. And it just so happens that these kinds of models, well, they fall short in the context of complex systems. And I think in order to really fully grasp the novelty of complex systems and chaos, you actually need to learn to think a little bit like a physicist. So obviously these two sessions are not going to be enough to give you, a full undergraduate's worth of theoretical physics. But what it should do is give you some feeling, some sense of what kind of models physicists were working with up till the 60s and 70s when chaos and complex systems were introduced. It will also be the occasion of asking ourselves the question, so what even is a good model in the context of physics, right? How do we quantify that? And we'll see that this is a question that has a simple answer in linear systems, so in non-chaotic systems, and it has essentially no good answer in complex or chaotic systems. The fourth session will be on feedback. So feedback is a very key concept in complex systems. It's an idea that you're all more or less familiar with, at least on a qualitative level, right? You've all seen, diagrams with, interactions looping back on themselves, right? So feedback is a very simple but crucial, really, dynamic in complex systems. I'll be drawing from examples a little bit in engineering, a little bit in earth systems, so that you get some, again, some understanding of how different types of feedback produce different types of dynamics. Okay, so these two sessions, for the moment, these are just words for you, right? So the session 5 is going to be about dissipative chaos and strange attractors. Mainly, I want to introduce you to some of the slightly odd vocabulary of chaotic systems. Session 6 will be Hamiltonian chaos and islands of stability. So we'll see what all this is about, huh? And session 7 will be about bifurcations and universal roots to chaos. So again, bifurcations, not going to explain what this means now, but this bit I want to tell you just in a few seconds. So the idea is that chaos came about in a very wide variety of fields, more or less simultaneously. Basically, people working in biology, working studying the evolution of population dynamics, people studying the weather, people studying just mathematical mappings, they all more or less came to chaos around the same time and in more or less the same ways, which is actually very surprising considering how different the systems these people were studying were. And this is one of the main and actually most fascinating aspects of chaos. It's universality, meaning that it doesn't actually matter whether you're studying rabbits, the price of cotton, or a phase transition. You will actually be able to use the same kind of reasoning and the same kinds of models to study all of these things. This is what's known as universality. For the last session that we'll be doing in person, I haven't really yet decided what we'll be doing. Basically, I have a few special topics in mind, and by session 7, I'll have some kind of understanding of what motivates you and what you find most interesting. Also, feel free to actually tell me. So depending on whether any of you have any programming background and just any desire to program, we can do some kind of like hands-on Python work to get a feel for how a chaotic system behaves when it's simulated. We can study chaos in astronomy, which is more or less my specialty, really. So chaos in the orbits of stars, things like that. And then there's a kind of like special topic which is kind of amusing. This one's very much not my specialty, but still we can find interesting things to say about it, which is like chaos every day. So there are all kinds of like weird little aspects of our lives which are in fact dominated by chaotic dynamics. A lot of the physicists in the 70s and 80s had a lot of fun with this. You can find like a myriad of articles on chaos and traffic jams, chaos and dripping faucets, and my favorite, which is chaos and jet lag. Like I've arrived in India yesterday. I'm currently a little bit jet lagged, and I might have time to explain to you why jet lag might actually come from chaotic dynamics. Okay, so these are sort of the things that we might be studying in our final session together, and I'll be awaiting your feedback really to figure out what interests you most in these like suggestions. Also, by session 7, you should have other things that you might suggest we study in the last session. So the final sessions, the remote ones, these will no longer take the form of proper lectures. Mostly because I find that with e-learning, lecturing at a screen is not terribly useful. What would be best would be for us to basically, I think we have 4 or 5, maybe 6 sessions together remotely, and the idea would be that we pick a bunch of topics, subjects that you want to explore, and kind of work collaboratively on this stuff, right? So have a more sort of project-based and special topics focused approach to the remote learning part. Coursework itself will take the form of just essays on the topics we'll cover in the final part. Though this bit is still a bit of a draft because I don't really know quite yet, what I should expect you to be doing in this course. Like certainly it won't take the form of a traditional, problem-solving physics exam. I think definitely the form of essays is what will be chosen. But apart from that, this is sort of the rough outline, right? I'll see also if you really have like, if you're very reluctant to work in this slightly like inverted way, then we can also have more of a lecture-based function. Well, we can more function on a more lecture-based basis in this part of the course. Not sure here. Okay, so this bit I'm hoping will take no longer than say 10-15 minutes. I'll tell you a little bit about me, and then I'd like to make a quick round of the people present and ask you a little bit about yourselves. So, as for me, I'm Théo Le Bret. So I prefer that we be on a first name basis. This is you're mostly, all the students. I'm guessing all of you, apart from a few of you, most of you will have already done undergraduate level work, right? So when I work with master's students, I tend to work on a first name basis. So I studied astrophysics in the UK mostly, and I'm currently in France teaching physics. So this has been very much a constant in my life. The thesis I worked on really was on galactic dynamics. So the specific problem I was working on was how the evolution of galaxies affects the distribution of dark matter in the halos of galaxies. So maybe at some point we can talk about this a little bit. So chaos isn't really the primary focus of the work I did as a grad student, but it kind of came up again and again, and because it kept coming up, and I kept finding it very interesting, and I thought that this would be basically a good occasion to share my love of chaos with you, and yeah. So essentially, that was also around the time I figured out that I actually wanted to try and come up with the course that would be suitable for people who are non-specialists, but who are not, beginners in education, right? So, which is all your case. You already have a very fairly long education, but not necessarily specifically in physics. And which is kind of a tricky situation, because usually in physics you do one of two things, right? Either you're teaching a physics course, in which case it's full of differential equations, and well, the students in front of you have a mathematical background, or you do pop science, which is essentially assume no mathematical background at all, assume no particular higher education, and just basically have very image-based. Image-based explanations. I'd kind of like to steer a middle between these things, right? So I don't want this is not going to be a pop science course. I will actually be introducing the full concepts, and I will be relying to some extent on mathematical models. However, whenever I use a mathematical model, I will fully explain the physical and conceptual content of the model, and I don't expect you to basically use the model as a mathematical model. I want you to be able to interpret it and gain an understanding of it, really. So this is sort of an experimental lecture course, right? Neither pop science, neither full physics lecture. So I'm very much looking forward to your feedback on all this, by the way. I really do need all of you to raise your hands and tell me to slow down if the mathematical bits start getting too involved, or else even just say if it gets too pop sciencey for you, then go ahead and tell me that we should delve deeper into the mathematics. So first of all, before we start on this history of chaos, really we need to understand what physics looked like before chaos, right? So this is the very the very beginnings of physics as a separate science, before it was just a kind of sub-branch of natural philosophy. You get, well, astronomy was the eldest of the physical sub-branches, and so you get people like Kepler, who spent decades mapping the orbits of planets around the sun, making some getting some broad understanding of how planets orbit the sun. You maybe remember from high school physics Kepler's laws, the planets are on elliptical orbits. A few things about the speed of rotation around the sun, and the periods and how they relate to the radius of the orbit, right? So these were Kepler's laws. So Kepler's laws are really empirical laws, right? So he didn't do any mathematics. His whole thing was he inherited a whole bunch of data from his master Tycho Brahe, and used this enormous trove of data to just derive empirical laws, right? So he just noticed patterns in the way that the planets moved. One of his main contributions really was a sort of aesthetic one, right? In that basically up till Kepler, very stringent efforts were made to model the orbits of planets around the sun as circles, right? And when circles didn't quite fit, they did what is known as epicycles, which are circles within circles, right? So these were the old models, which were based on the idea that the universe being God's perfect creation, then everything should be circular because circles are perfect, right? It's the perfect geometrical shape. Therefore, all the planets should be orbiting on circular orbits. And Kepler sort of struck a blow to that model, right? He said, well, no, actually, empirically, it seems that they're on ellipses, so too bad for us, I guess. So this really started out, started a kind of revolution in the sciences and in astronomy in particular, but still very empirical, very data-based, we'd say today. Newton's great success was in retroactively predicting what Kepler had only observed. Basically, Newton set out to write a few very simple laws of dynamics. You might remember, Newton's second law, perhaps, from high school education, force equals mass times acceleration. So what he said was he set down a very simple theory, right? So dynamics, maybe this is the first thing that should be explained, right? Dynamics is the study of forces, more precisely the way that forces affect the motion of systems. And up till Newton, there was only a very qualitative understanding of the link between motion and forces, right? So Aristotle, for instance, believed that essentially what forces did was that they acted directly. They were responsible for the speed of objects in the universe, which is sort of like the way most people intuitively think about forces, right? If you see something moving, you're thinking, well, something's making it move. It has speed because it's interacted with a force. As it turns out, this intuitive understanding is wrong. Something you can have motion without any kind of interaction, right? That was Galileo's insight. So the idea what became known as the principle of inertia, right? That an object that has no force applied to it will continue in a straight, regular movement, right? Again, maybe vague memories of high school physics. And what Newton said was, well, yes, actually what forces do is they make objects accelerate. So I'm just going to write down the equation as you know it, basically. Well, maybe not quite as you know it, because I'm using a vector here. And really what this means is if you have, for instance, the sun here and the earth here, then basically this here will be the gravitational force from the sun, well, applied to the earth by the sun. And as a result of that, the movement of the Earth will be sort of, an ellipse like that, with the acceleration going that way. So the little arrows here just mean that, well, mathematically it's called vectors. Really what it means is that they have a direction. So this is a very simple equation, right? This is Newton's second law, the fundamental principle of dynamics. The funny thing is, during this course, and the study of chaotic and complex systems, well, at least in mechanical systems, there's nothing more complicated than that. There's not a more complicated law giving rise to the complexity in mechanical dynamical systems. It's just Newton's second law. Because this is the problem. When Newton tackled the Earth-Sun problem, he had a great success, right? He was able to predict exactly the types of orbits that Kepler had observed. So just based on this law, force equals mass times acceleration, and based on on Newtonian gravity, that the gravitational force is proportional to the inverse square of the distance. Just based on these two insights, Newton was able to predict that any two bodies orbiting one another would move in precisely the way that Kepler had observed, which is really an incredible success, right? This is the first time that a physicist has used mathematics to just explain astronomical phenomena in a completely satisfying and self-consistent way. So I'm just writing down the second thing here, which is just the expression for Newton's law of gravitation. But this is probably something you've already seen, right? So this is the radius of the orbit. So yeah, two small equations, which you could have studied in high school. They allow you to predict with complete accuracy the type of motion which is known as the motion in a central force. So what these laws allow you to predict are things like what is the shape of the orbit going to be? How fast the planet's going to be rotating around the sun and on different bits of its orbit, right? And this is again something that's taught, in maybe last year of high school, first year of physics undergrad. You learn how to compute such orbits, right? And you do it, and it's not that there is no uncertainty at all in these problems, right? The orbits are known as accurately as you know the initial conditions, meaning that if you know the speed and the position of the planet at one point accurately, then you will know the position and speed of the planet accurately on every other point of its trajectory. And this became this idea, right, that if you know the sort of initial conditions, right, of a system, if you know its speed and position at one point, then Newton's laws will predict the entire motion of the system like clockwork, right? Really, this was actually the preferred metaphor, right, for physics at that time. It was known as the clockwork universe, right? The idea that as long as you know what the first cog does, then everything just follows beautifully, mathematically, with zero uncertainty. The only thing was that, if you knew the position and the speed inaccurately, then you would have some observational inaccuracy in your predictions, right? But that's something we can all come to grips with, right? That wasn't shocking to 18th and 19th century physicists. But they very quickly, they very quickly adapted Newton's laws and made it a little bit more complex, right? Yeah, sorry. Oh, so L here is angular momentum, basically. So this quantity, this is mass times velocity, this is radius, and if you multiply these two, you get L, basically. So L is the angular momentum is sort of the quantity of rotation, in a way. So, classic example of what angular momentum means. I don't know if you've ever done this experiment, but if you're sitting on a chair like that, and you turn like that, so basically I'm spinning, my angular momentum is conserved, so if I'm spinning like that, I have a certain amount of angular momentum, but because here I've reduced what's known as my moment of inertia, which means this conservation of momentum is what means I spin faster as I bring my arms closer. So concretely what this means for planets is that if you have, for instance, a gas disk around here, and the gas can dissipate some energy, then what's going to happen is as it moves closer to the center, it's going to spin faster and faster. You may have seen this sort of thing in images of black holes, for instance, with big shiny heated gas around them. Though this is somewhat tangential to the rest of the lecture, but yeah, angular momentum. Okay, so this is the situation in the 19th century. We know about Newton's laws. The two-body problem is solved perfectly. So now the question is, well, obviously there are more than two bodies in the solar system. We have the Sun, we have the Earth, we have Jupiter, Saturn, etc. So what people started to do was they used Newton's laws, had the simple two-body interaction, and then added little bits, right? They were like, okay, so we have the Sun-Earth system. Now what happens if I add a small planet like Mars, not too far from Earth? Obviously the interaction coming from Mars is much smaller than the interaction coming from the Sun, but it still has its effects can still be a little bit perceived. And this became known as perturbation theory. So we'll come back to it later, but this became quite an important aspect of classical mechanics. That you start out with the first assumption, which is that the sun is the only thing that matters in the solar system. Everything just turns around the sun. That's your first level model, your 0th order approximation, as you'd say in perturbation theory. But then you add something. You say, okay, well, obviously that's not true, right? Obviously, Jupiter is a pretty huge planet. So we will actually want to add Jupiter as a perturbing influence on the orbits of other planets. It's a much smaller influence than the sun, but it's still important. So you add it to your model. And you can see that it does have a noticeable effect on the orbits of other planets. Now, one of the greatest successes of this kind of clockwork model was the work of Le Verrier. So Le Verrier was a French astronomer who did exactly what I'm describing here. So he computed the perturbations due to all the planets that he could see. So he did it with, well, at the time were known Mercury, Venus, Mars, Jupiter, Saturn, and Uranus. And what he noticed was that when he added up all of these perturbations, there were still unexplained anomalies in the orbit of Uranus, basically. And what Le Verrier did was he just said, well, my calculations can't possibly be wrong, so there must be another planet. And he computed accurately what kind of orbit this planet would have to explain the perturbations. And he then sent a letter to the Paris Observatory and said, on this day, point your telescope here, you'll observe a new planet. And they did. So this was a huge, just an incredible success, right? Like a planet that had never been seen before, that was only perceived in the mind of Le Verrier because he saw some anomalies that his calculations couldn't explain in the trajectory of Uranus, right? So this was really just a tremendous success for the clockwork universe, right? It's like just based on a completely deterministic model, you could, as long as you cranked your mathematical equations and didn't make any mistakes, you could potentially just, predict the existence of something that had never even been observed. Just incredible stuff. But unfortunately, didn't last. Because you see the perturbation model that Le Verrier used, which is the idea that you have one big thing and then a series of smaller things, and what you do is you treat them in descending order, right? So if we go back to the planets, what you do is first you take the influence of the sun, then you take the influence of Jupiter as a small perturbation on that, then Saturn, and then you add smaller and smaller perturbations, and hopefully all of this becomes like a good model, right? But you run into trouble very, very soon. Actually, you run into trouble as soon as you reach what's known as the three-body problem, which is a slightly different problem than what we've been tackling here. It's like, this time imagine it's not the Earth, the sun, but just 3 stars, for instance. So these are stars. They all have the same mass, just to simplify the assumptions a little bit. So this is the center of mass of the 3 stars. So you have 3 stars, and they're interacting, again, only with this. They're interacting through Newton's second law and through Newton's law of gravitation. The equations haven't changed, right? The dynamics are still based on the same exact equations. But here are the trajectories. So green, red, blue, these are the trajectories of the 3 stars in this system. Now, this isn't neat. This doesn't look very good. This is, well, chaotic, basically. As you can see, there's no, you can write down the equation of a circle, you can write down the equation of an ellipse, you can write down the equation of a triangle, a line. So there are shapes which have well-known mathematical equations describing them. Well, these are clearly not, right? This is nonsense, right? Look at this, what this thing does, right? It goes over there, it kind of loops back, loops right back like that. This one does a weird squiggle here. It's just incredibly confusing stuff, right? And this is the second most simple system you can come up with after the two-body problem, right? So this is something which is a pretty classic thing happening in physics, right? It's like you know how to solve exactly for the two-body problem, so the two-body problem holds no mystery whatsoever. But as soon as you add a third body, boom, everything collapses. And basically, the three-body problem was an open question in physics in the 19th century, because everyone knew that the trajectories in the three-body problem were weird, but people still clung to some kind of hope that you could describe them with, neat closed equations. And it actually became a competition, right? There was an essay competition based on this question, on solving the three-body problem. And essentially Poincaré won the competition by answering, no, can't be solved. So his answer, so he won the prize, but he won the prize for proving that the question was pretty much intractable, right? And really, the reason people were interested in this problem in the first place was because they were interested in a more basic question, which is the solar system stable? Because, this is the way that we see the solar system, right? Sun and everything orbiting around it, right? But this isn't actually how it works, because all of these planets interact with each other. And actually, at the time of Poincaré's life, it hadn't been proved that these interactions were stabilizing the solar system. For all we knew, the interactions between Venus and Jupiter, or Jupiter and Saturn, actually had a destabilizing influence on the solar system. So really the question was, so the solar system, is it stable? And the answer to this day is probably most of the time. But actually, we're fairly certain now that there were times in which the solar system was also chaotic. So this is one of the first questions that we'll be thinking about in chaotic and complex systems, right? It's like, you have something that looks very regular, looks very predictable, but actually, is it always going to be the case, right? And what we believe today is that there was in fact a time in which the solar system was deeply unstable, which is probably one of the reasons why we ended up with a bombardment of asteroids a few billion years back. There's another textbook example of chaos, which, if I can actually, oh, no, crap. Well, so the other textbook example is what's known as a double pendulum. So a double pendulum is just metal rod, hinge, metal rod, right? So everyone knows what a pendulum does, right? It goes click, 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 literally clockwork, right? This is how we used to make clocks back in the days. Now the funny thing is that if you add a slight tweak to this, instead of having just one pendulum, you add a little hinge here, well, this system, again, its dynamics is described exclusively by Newton's law and by the interaction between the Earth's gravitational field and the metal ruler there. Well, this system turns out is completely chaotic. So the blue lines here, they represent the trajectory of the tip of the double pendulum. Now, as you can see, this is not a complicated system, right? This is something that has 2 degrees of freedom, right? To fully specify this system, you need to specify one angle here and one angle there, and it's governed by one law of physics, Newton's law. And yet, it has incredibly confusing dynamics. So I'm going to try and show you what it looks like for real. If I can, there we go. Yes, allow. So there's actually, well, yeah. Fine. Can we skip the ad? No, apparently not. Okay, great. Now that we know which toothpaste we're going to buy, let's watch this pendulum. Right, so this, for the moment, is just a simple pendulum, right? Metal ruler, one hinge here. And, well, no spoilers, but not a very interesting system. Okay. So this, by the way, one of the first physical systems ever studied by Galileo, and then most physicists afterwards. This, as it turns out, is really the basic thing which was studied in dynamical systems. Now what's happening is here, we're just unscrewing a little screw, so now it can hinge like that. And now look what it does. And it occasionally goes into some very, there we go, very weird little, sometimes it just sticks around and spins on itself for a while, there we go. Now, yep, just absolute nonsense. This is, Now, the point of this is twofold, right? A, I don't think many of you would have intuitively predicted that such a simple system could behave in such a complex fashion, right? I mean, there are bits of its motion where the first half of the ruler just stops, and lets the second one spin for a while. Then it resumes behaving more or less like a regular pendulum. There are bits where it just does that, and it's more or less predictable. Then suddenly it becomes chaotic again for no good reason, right? And another thing that you could do, so this isn't done in this experiment, but it's an interesting experiment you can make with these, is you can take two double pendulums, start them out in almost the same starting position, let them go, and after a few seconds you realize that they're not doing the same thing at all anymore, right? So this is something we'll come back to, which is known as sensitive dependence. Okay, so what's the idea here? We have two very simple systems which are really small departures from very well-known textbook physics examples, right? This is just a slightly modified pendulum. This is just slightly more complicated than the two-body problem. And yet, that just a slight complication, and you immediately run into chaos. So, these were really things that people were thinking about in the 19th century, but nothing really was made of it, right? Poincaré did come up with some broad mathematical tools which were of use about a century later, but chaos wasn't really born in the 19th century. Chaos was really born in the 60s, 70s, and 80s. In particular, in the 1970s, people were starting to study models for population dynamics. Now, population dynamics is a fairly straightforward affair, well, at least when you're trying to model it easily, right? So you have a population of rabbits. What happens is, when there are few rabbits, the rabbits breed, you get more rabbits. At some point you get too many rabbits, so the rabbits die off. So these are the simplest facts that your model needs to capture, right? It needs to capture reproduction and it needs to capture starvation, because the rabbit population can't grow infinitely, but it obviously has a tendency to grow and then to collapse if it becomes too large. So that was the idea behind one of the most simple models for population dynamics, which was called the logistic map. And Robert May, in the 70s, studied this thing, and he gave his paper a beautiful title, Simple Mathematical Models with Very Complicated Dynamics. And this is the example in question, right? So the equation governing the logistic map was exceedingly simple. I don't know if you remember it, so I'll write it down again. So if x is the population and n is the year, then the population on year xn plus 1 is equal to r times xn times 1 minus xn. So what does this equation say? So this is the population next year. xn is the population this year. And this is a parameter. And this parameter basically tells you, well, it's related to the capacity of the ecosystem, right? It tells you how quickly you're reaching the limit for starvation. So, this is a model that has one variable, the population, one parameter. So it's very difficult to think of a simpler model really for population dynamics, because if you only had this term, right, this would be the growth term, right? The population next year is proportional to population this year. If you only had this bit, your population would grow indefinitely, right? So if this year's population is 2, next year is going to be r times 2, the year after that r times 2 times 2, etc., etc., etc. So with this bit, the population grows indefinitely. So you need at least one other term to take into account the fact that the rabbits do have to die off at some point when they start starving. So that's the model. This is what's known as the logistic map. So in mathematics, map just means that you relate discrete quantities. Population this year, population that year, population next year. So this logistic map, as you can see, is an extremely simple system. I mean, I don't think you really even need any real mathematical understanding to see what this tells you, right? It has a growth term, it has a decay term. That's it. Nothing more complicated. But, well, this thing depending on the value of the parameter here, can have some very complicated dynamics. So this is the evolution of x with time, right? So this is just, we've iterated this map 1, 2, 3, 4, all the way up to 100 times. And, there are patterns. This isn't, it's like the double pendulum, right? There are bits where it behaves more or less like a regular pendulum. So, and these look almost like regular oscillations. We know that when it reaches certain positions, the population collapses, which is normal, right? If you suddenly have a population of rabbits very near the capacity of the whole ecosystem, then next year's population is going to collapse. Much in the same way that there were certain positions of the pendulum where we knew they would start, spinning and doing this thing, and then we knew that there were bits of the pendulum's dynamics which were more or less regular. And this is a classic feature of chaotic systems, right? It has some bits of it which are predictable, but its evolution as a whole really isn't predictable, right? So that was one of the first insights, one of the first inroads into chaos, right? Was the study of a mathematical system that was supposed to be a very simple model for population dynamics. Then, in the 70s, oh wait, sorry, forgot something. So, what was the broader question really that people were trying to answer in this, right? Is that in the 60s, the broad consensus in ecology was that populations tended to find balance, right? So ecosystems were complicated systems with some feedback, with complicated interactions between species in climate, and the idea, the broad understanding was that all of this kind of met in the middle so that the world was in balance, right? And people expected that populations would probably oscillate a little bit, but in a kind of regular way, right? In the same way that temperature oscillates all year round, or that the tilt of the Earth's axis oscillates. So these are regular, what are known as periodic oscillations, right? That's what people expected, because people had this sort of inbuilt bias that the world is in balance and equilibrium, and so people expected regular, periodic variations in populations of animals, for instance. And unfortunately, the conclusion was that even a very simple system of population dynamics ends up having some very complicated dynamics. And so the question arose, which is well, so is there even such a thing as ecological balance, right? Is this something, are we missing a crucial element really in our study of ecology? Because for instance, people used to assume that the only way you'd have population collapse was if something awful happened externally, right? So meteor, volcanoes, these were the usual mechanisms to explain mass extinctions. But actually what this tells you is that, well, I mean, the rabbit population sometimes collapses for no particularly good reason. It's just one of the possible solutions to this simple mathematical equation. Okay, so if you recall, one of the questions from astronomy was, is the solar system stable? And the answer was no, probably not. At least, well, as far as we're concerned, it is, right? Over the next 10,000, 100,000 years, but probably over the course of hundreds of millions of years, probably not stable. Is there such a thing as ecological balance? And, well, the answer is, it depends. Do we believe our models, basically? If we believe very simple models, the answer is no. But obviously, we shouldn't always believe our models, right? And this is one of the things that is going to come back again and again in the study of chaos, right? Is that we should always be careful and realize that what we're talking about here is the behavior of a model. Now, the fact that this model does, in fact, look like a real population evolution does not necessarily mean that the population's evolution is driven by something as simple as that, right? And it almost certainly isn't, right? If you were studying the population of rabbits in a garden, then obviously, things like weather, things like, year-round temperature, whether the farmer was at home or not, all of these things will obviously impact the real world. And one of the questions that chaos will keep asking of us is, okay, so obviously this is a very vast oversimplification of reality, but does it actually capture the main features? And can we draw, useful insights from models that are vastly oversimplified? That's something that we'll come back to quite regularly. Okay, so the second branch that led to chaos was population dynamics. And then the third one, which is really, I think, this is the most obvious one for a physicist, right, is the weather. So, as you may or may not know, the weather is difficult to predict. Today, with very fancy models of meteorological evolution, we can get accurate weather models for, 4 or 5 days, maybe a week. After that, they're very unreliable, and no one can actually predict the model can predict the weather a month from now. Which is weird, right? Because you'd think, well, we can predict the climate a few hundred years from now, but we can't predict the weather 5 days away, right? And as we'll see, there's a very good reason for that, right? So that we're not at all talking about the same kind of dynamical systems, right? But nonetheless, so the problem with weather forecasting is very ancient, right? Humans have relied on some kind of weather forecasting basically since we've sailed, right? And it used to be that weather forecasts were very much like a few hours in advance. So you had a barometer on your ship, and whenever the pressure dropped, you kind of crossed your fingers and hoped that nothing too bad would happen, but probably a storm was coming your way, right? And that was more or less the extent of weather forecasting for a very long time, right? Just you could record local changes in pressure and temperature that would give you some inkling of what might be coming your way. And obviously, in the 20th century, we started trying to get much more elaborate models. And in particular, we started to try and get models based on atmospheric physics. Because really, in a very simplified way, what's the weather? The sun heats the earth, so you have land surfaces, water surfaces, and what happens is that the earth and the sea get heated, they heat the air above it, hot air goes up because it has higher buoyancy, and then as it goes up, it cools, it falls back down. So this is a problem which has a very, very respectable pedigree in physics. It's what's known as convection. So convection is something that you've probably observed, if you boil a pot. There's a lot to be understood and gained in physics by looking at pots boil. So the idea is that you have a plate here which is at a temperature that is hot, and a plate here that is at a temperature that is cool. So these are what's known as your boundary conditions, right? So in the case of a pot of water, this is your heater, this is the air around it. In the case of the atmosphere, this is the earth or the ocean, this is the upper layer of the atmosphere. So what happens is that you get hot air here, which rises. It reaches the upper atmosphere, cools down, comes back down. And you get this like that and like that. So this is actually the most simple model for convection, right? You have one circulating cell that does something like that. And the trouble is that you can write down equations for that. You can solve them exactly. And then as soon as you start increasing the difference in temperature, funny things start to happen. Because if you think about it, there are different regimes, right, to this evolution. If the difference between hot and cold is very small, then actually what will happen is you'll just get a homogeneous temperature gradient, right? So you won't even get really circulation. What you'll get is like just the liquid or the fluid going from hot to cold, but not moving around, right? As you increase the temperature gradient, you start having these cells circulating. As you increase it a bit more, what's going to happen is that this isn't going to rise to the top. This is going to go here and sink back here, and you'll have a second cell here, and another cell here, and eventually you just have cells upon cells, worlds upon worlds. So this is really the basic model that goes into what's known as the Lorentz model. Lorentz was just trying to get a very simple understanding of how weather worked. So he was saying, okay, let's model the atmosphere with 3 parameters. So we get the temperature difference. So how big is the difference between cold and hot air? We get the speed of flow, and we get a sense of how layered the system is, basically. So this is a 3-variable model. We'll come back to it and study it more precisely at some later point, right? So, what does this model tell you? Well, it tells you that actually even such a simple system has, well, you guessed it, complex behavior. So this is the time evolution of the x variable. So the x variable, as I recall, is the temperature difference, right? It's how it quantifies how far from a simple linear, well, okay, so x quantifies how steep the difference in temperature between the hot and cool boundaries are, right? And this x variable just, starts out oscillating. So this looks like a kind of regular oscillation, and then, it does what chaos does. Actually, you very quickly realize there is no repeated pattern. It sometimes does a few loops around something that looks like a stable equilibrium point, and then goes right back down and just continues in its very unpredictable evolution. Now, Lorenz was famous for two things. First, he was the one who really first came up with these chaotic models and studied them. So he started studying them in the 60s, so it predates Robert May's work. And one of his earliest works on the topic is, it was an article that was very, poetically called Deterministic Non-Periodic Flow. Now, I'm not sure that this evokes anything much for anyone. This is, okay, I reckon to a non-physicist this doesn't even say that you're talking about the weather. This is in fact what you're talking about. But then, in the 70s, when he got slightly better at communication, he did a small conference, and the title of the talk was, "Does the flap of a butterfly's wings in Brazil set off a tornado in Texas?" So this is actually what's known as the butterfly effect, right? When we talk about, and this has become a colloquialism, right? The butterfly effect is the idea that a very small difference in initial conditions can lead to a very dramatic and very large shift in your predictions, right? Now, it has to be said that quite often this is interpreted as meaning small things have big consequences. This is not what this means, right? Because you could also phrase it the opposite way around, it would still be true, right? You could say that the flap of a butterfly's wings prevents a tornado in Brazil, or also just that the tornado in Brazil will mean that the butterfly, flutters its wings miles away, right? So this isn't a statement about small things have big consequences. This is a statement about uncertainty, right? This is telling you that if if I start out of here and I shift my initial value of x by the flap of a butterfly's wings, then the evolution of this thing might be totally different. So this is something which is known as sensitive dependence on initial conditions, and will be the topic of the next slide. But if we rewind a little bit and take a little bit of perspective here, this is now another question, right? The question here, the question that meteorologists were answering in the 70s, was, are medium-term weather forecasts even possible? So this was really what Lorenz was interested in. He wanted to know, is it possible? Can we predict the weather a month from now if we had enough computing power, if we had enough time? And in the 60s, people thought the answer was yes, right? People thought, as long as we make our models sufficiently close to reality, right? If we have complex enough models, and we have enough computer time and computer power to just run these models, then we should ultimately arrive at some very good weather forecasts. And what Lorenz said was, actually, this isn't possible even in principle, because he took a very simple model, and he showed that even with this extremely simple model, well, everything became unpredictable very quickly. And in particular, what he showed was this thing called sensitive dependence on initial conditions. And this is what we mean. So here, this is again the Lorenz system, right? And we're still looking at the evolution of this temperature difference, right? Well, the temperature gradient. So here, there are actually two lines. You can't see them because they overlap completely, but there's a red line and a black line. So as you can see, they start out pretty much on top of each other. The system evolves, and they stick around together for a while. As you start reaching this point, you start seeing the two lines are slightly distinct. Here they become a little bit more distinct, and then at some point what happens is the black line just stops following the red line at all. And by the end of the evolution, well, I mean, you couldn't even say anything qualitatively right about the difference between these two things, right? Like, it isn't the case that two things that started out close remain close, right? This evolution, they start out very close, and then after a while, the predictions from these two almost identical models become completely different. And this is what's known as the butterfly effect or sensitive dependence. What this means is that a very, very small uncertainty in your initial state will mean that by the end of it, your forecast is useless. Actually, it's even worse than useless, because if you believe your forecast, you're going to make very large mistakes. So your forecast becomes not only not useful, it becomes grossly misleading. And this is actually something that Lorenz discovered by accident. So he was running his very simple model in his computer. And basically the way a computer works is, you give it some input, it has a program to treat the data, and it gives you some kind of output, right? Now, what Lorenz did was he fed a few numbers to his model, it cranked them out, and then at some point there was a bug. So he thought, well, I don't want to restart the program from the start. He thought, I'll restart it from the middle, from the place where it stopped. And so he just took the output of of his first simulation and fed it back into the computer. So you can imagine that he had the first prediction, which was the red line, and then in the second prediction, he fed the same numbers as the initial thing, but he made a mistake. Basically, instead of using double-digit accuracy, he used single-digit accuracy, meaning that there were a few decimal places that had gone missing, right? So he put it in, and voila, basically, he realized that after a little bit of time, his two models had diverged completely. And he was very surprised by that, because again, this is not something you'd expect as a physicist. Physicists tend to work with what are known as linear models. In linear models, the response is proportional to the perturbation, meaning that if you look at a pendulum, it swings, and if you perturb it slightly, then it's still going to remain more or less the motion of a pendulum, but with a slight deviation. And essentially there's a proportionality between how much you perturb the pendulum and how strong the response is going to be. Well, in the case of chaotic systems, that's no longer the case, right? What happens is a very small perturbation can have very dramatic effects. So, this now gives us a kind of overview, right, of what chaos means. The first thing is, chaotic systems are deterministic. At no point have I given you equations or laws of dynamics that introduce randomness. There is no randomness here. These are all Newton's second law, all the laws of hydrodynamics, or some very simple population dynamics. At no point did I say, flip a coin and see what happens, right? Because there are such models in physics, right? For instance, when we study economics, quite often we add what are known as stochastic variables, variables that are random, right? So, for instance, if we're looking at market evolutions, then we will, we believe that there are some random fluctuations in those that you don't really need any model to explain. We just say, well, it's just noise, right? So in order to fit our models to the data, we introduce randomness. We say, well, we take a deterministic model and add some randomness to it. Here, there is no randomness. This stuff looks random and looks complicated, but the law it follows is completely deterministic. Meaning that if we knew the initial state perfectly with infinite accuracy, then we would actually know the final state with complete accuracy and prediction, with a perfect prediction. Now, obviously, the problem is that no one knows how to get a perfect observation. So actually, in a chaotic system, our predictions can be very quickly rubbish. The other thing is going to take a little bit more time to explain, and I think I'll have time to explain it more fully in the next 2 lectures, right? Basically, the reason this happens, that despite the fact that they're deterministic, they have very complicated behavior, is because they are non-linear. So, I'm going to start introducing this idea now, but we'll get a fuller understanding of it at a later point. So, at its root, what linearity means is proportionality. For instance, if you have here, so this is a wall, this is a spring, and this is a little mass at the tip of this spring. Well, as you know, if I pull the spring, there's a force going this way. And basically, the law that governs this force is very straightforward. The force is equal to kx. So if this is the x-axis here, and k is some constant that depends on what your spring is made of. Okay, so this is just a mathematical formulation which tells you something very simple. If I pull the spring 1 centimeter and then pull it, I get a certain force. If I pull it 2 centimeters, I get twice that force. If I pull it 4 centimeters, etc., etc. The force acting on the object here is just proportional to how far away I've pulled the spring. This has a visual representation, right? If this here is how far I've pulled the spring, if this is the force, then what the model tells you is that it looks like that. Linear, it's a line, basically. And the slope of the line is proportional to k, where k is just a property of the spring. If this is a hard spring, then k is large. If this is a soft spring, then k is small. Now, as we'll see in the next lectures, linear systems are really the bread and butter of physicists. Like, this is what you learn to do as an undergrad, right? You take a linear system, you study it, and then maybe you add a few complicated elements, but really the root of it, the basic structure, is linear. The problem is that even with this system, actually, it's not linear, right? Because look at this line. Technically, what this model tells you is that I can just pull the spring as far as I want, and the response of the spring will just keep getting bigger. I mean, do any of you reckon that this is actually what happens? And from your own experience with metal springs or elastic springs or whatever, I mean, what actually happens if you pull a spring too much? It breaks down. Basically, at some point your spring no longer pulls you back, it just starts breaking down. So you get something that goes like that. So at some point, the response of the spring doesn't go any higher, and then at some point something catastrophic will happen, you'll break the spring. So it goes to 0. So this is essentially the reason we study linear systems, is that most systems kind of look linear if you don't perturb them too much. Basically, anything looks like a line if you look close enough, right? If I zoom in, if I zoom in on this thing, like this bit really is kind of linear. And this is sort of the reason that physicists like linear models. You can make anything look sort of kind of linear if you look close enough. And this was the reasoning in most of classical physics for a very long time. It's just unfortunate that it doesn't always work. Okay, so this is what we mean by non-linear. Chaotic systems are non-linear, meaning that they live in this part of the world. So this is linear, and this is non-linear. Bless you. Also, well, this is, I think in the course outline I promised you that they mentioned this sort of stuff in Jurassic Park, so I'm going to have to live up to that. There you go.
Yeah. I really hate that.
The Tyrannosaur doesn't really set patterns or hard schedules, the essence.
From that there in chaos.
It's simply the ability of predictability and complexity. The shorthand is the butterfly. The butterfly flaps wings be taken and send the party that way instead of sunshine. And then I go to France, I did black. You don't do that in the glass bar. We're conducting an experiment. It should be still, the car bounce up and down. But that's a now, put your hand flat on a higher level. Now, let's say drop waterfall. Which goes up and roll off? Okay, now freeze your hand. Don't move. I'm going to do the same thing, start the same place again. Which way do you roll?
Let's say that.
So say that. Because tiny variations of the orientation of hairs and blood and vessels and infections in the skin. And never repeat. That's
Okay, so this is a kind of like, basically what Malcolm is explaining here, and so also his character is actually based on a real life chaos theorist. I think it was Feigenbaum, I can't remember which one, I'll check on that later. But basically what he's saying is, he's describing sensitive dependence on initial conditions, right? If we're going back to the example he's using is, right, a drop of water on someone's hand. And the idea is that the dynamics again is completely deterministic, because the trajectory of the drop of water on the hand is really due to just, well, gravity and the laws of fluid dynamics. There's no randomness occurring here, right? What does happen, however, is that basically the actual trajectory will depend very sensitively on which precise bits of the knuckle you're dropping the drop of water on. And this means that very quickly, if you drop two drops on nearly the same point, they might start out on more or less the same kind of trajectory, but this will diverge very quickly. And actually, for those of you who have an interest in data-based policy, basically, this is actually very important. This difference between the sensitive dependence on initial conditions that nonlinear systems have. I'll try and explain to you now, so that we can have some. We'll have some discussion about that, I think, at the next course, at the next lecture tomorrow. So imagine you have a linear model, right? But this is your model, this isn't the data. The real data, well, it looks something like that, right? You have error bars. So this represents the uncertainty around each data point. So this is F, this is X. And yeah, it goes something like that. So basically what you do here is, if you want to figure out, for instance, what the spring constant is, well, you'll fit a line through this. And you'll try to fit a line that goes as close as possible to as many of the points as possible. Maybe you'll have a few outliers. That always happens, right? Like, if this is real data, then you'll have, some of it will be a bit crap. But you have a very good way of quantifying how close your model is to reality. And also, there's a very straightforward answer. If you want to get better answers out of your system, if you want to get, just a better constraint on the spring constant, then it's easy. The only thing you have to do is either add more data points or get these error bars to be smaller. If my uncertainty comes from the fact that I've measured force with a crappy dynamometer, then I just get a better one, right? And get those error bars down a bit. And the idea is that, there's in a linear system, there's a direct relationship between how much I invest in reducing the error bars and how much better the constraint on my model is going to be. Basically, if I know, in a linear system, if I know the force 10 times better, then I will get a 10 times better estimation of the spring constant. So this is true of the linear part. This is no longer true of the nonlinear part, which is precisely the problem. Which means that it doesn't, in a nonlinear system, for instance, in the weather forecast, it doesn't actually pay to have 10 times more observations of your initial states, because that's not going to get you 10 times better prediction. It's not going to get you 10 times longer, a forecast with 10 days instead of 1, because of this sensitive dependence, right? So what this suggests is a completely different way of using models for forecasts. Rather than trying to pinpoint exactly where you fall on this line and running a perfect model once, what you'll do is actually you'll run several models starting out from more or less the same place, and you'll see how they all evolve. And this will tell you something much more useful, because if you start like 10 different models, you start them around the same point, and they all seem to more or less agree up to like a few days, and then they all start diverging. Like, this actually tells you something useful, right? This tells you that you have one part of your predictions which is robust, and another part that isn't, right? And getting 10 times more accurate initial conditions isn't actually going to tell you anything useful, because at some point everything will diverge, right? So I think the take home here is that there's a fundamental way in which you use models depending on whether they're linear or non-linear. In a linear model, what you want to do is pinpoint, get more precise observations, get more observations, and then fit your model as exactly as you can. In a non-linear model, what you want to do is actually use what's known as an ensemble of models, right? Which is actually how they do weather forecasting now. So medium range weather forecasting uses ensembles, meaning that you don't use one model, you use, say, 100 models, and you look at their behavior based on different types of observations. And this gives you much more useful data than, well, for predictions than the kind of standard old school, one model, one prediction way of doing things. Well, we'll get back to that. I think I think the more model and policy-based stuff, well, probably reserved for the special topics section. If this is something that is of interest to you, then I think maybe that would be a good thing for the for session 8, right? After we've done the kind of like broad overview of feedback and such things. Okay. So, I think this about concludes what I want to tell you today. First of all, do you have any questions? Okay. Well, if you come up with any questions, feel free to ask them at the start of the lecture tomorrow. I would say, so I haven't actually given you bibliographical references for this part of the lecture. Broadly, I've based my introduction on James Gleick's Chaos, and also on the Introduction to Chaos by Leonard Smith. I think you've all received a short selected readings list, maybe? Ah, okay, right. So tomorrow, I'll introduce as my first slide a few readings. Basically, I think the one that I really like. Well, it's not that I want you to read it. It's like I hope that you read it for yourselves, right? Because it really is great. Is James Gleick's Chaos: The Birth of a New Science, and yeah, I guess see you tomorrow then.